welcome back. In this lecture, we are going to discuss how to calculate partial molar properties from experimental data. So, let me first again start with the definition of partial molar quantities. Okay, so this is the definition. Now, in case the data are available, particularly for E, for a small change in E upon addition of n, small addition of n, then of course we can approximate it. Okay, we can represent this as simply delta E by del Ni. Okay, so if the data is available, it's straightforward, particularly when we add small amount of component in a given mixture. Okay. So, let me just do one example and then we try to take a case where this partial molar quantities for complete composition we would like to evaluate. So, this is a case where we have a binary aqueous solution of water and sucrose. So, let us assume that you want to prepare a binary aqueous solution by mixing 2 kgs of sucrose in 100 kg of water. Okay. So, 2 kg is relatively small compared to the amount of water present. Okay. And you have been asked to find out the volumetric change or the partial molar volume of 2. Okay, that means what is 2, which in this case we are going to say 1, this is 1, component 1 and this is 2. Okay. So, what is partial molar volume of 2 sucrose in this condition? Now, let me just write down some of the properties of sucrose and water. So, let us say that the solution mixture at 20 degrees Celsius and 1 bar. Okay. So, the density at 20 degree Celsius and 1 bar is 1.0060 kg per liter. Okay. And the molecular weight for water is 18.02 gram per mole. Molecular weight of sucrose is 342.3 gram per mole. So, these are the information given to us. In addition to this, we have given that pure water at 20 degrees Celsius and 1 bar. So, this is the condition of the solution is 0.9982 kg per liter. Okay. So, how we are going to find out the partial molar volume of sucrose? That is a question. So, now we do not have anything else. So, what we can see that the amount of sucrose we are adding to the solution is extremely small compared to the solution. Okay. That means delta N2, okay, because 1 is water and 2 is sucrose, is extremely small. So, in this condition, if you look at again the definition of the partial molar volume, this is del V by del N2 at a constant temperature, pressure, and since it is a binary mixture at a constant N1. So, the water is basically kept constant and we are changing N2. Now, considering very small amount of the change, we can approximate this as delta V by delta N2. Okay. Now, what is delta V here in this case? Is basically change in the volume of the mixture. Okay. So, upon addition of this small amount of sucrose. So, this is going to be V mixture minus the original or the volume contained by the water itself. Okay. So, V mix minus V 1 divided by delta N 2 or simply N 2 in this case. Okay. The amount total added. Now, what is a V mix? So, V mix is how we are going to find out V mix? What are things which are given to us? We have measured the density of the mixture and we are aware of the molecular weight of the components. So, we can make use of that. We know that volume is nothing but mass divided by density. Okay. So, this is going to be M1 plus M2 divided by rho mix. What about V1? V1 is rho 1. Okay. So, M1 is basically this, mass is given here, M2 is this, and rho mix is basically this. Okay. This is the system rho mix. So, and similarly we have been given M1 and as well as basically the rho 1 of the water. So, considering this, you can plug in here. Okay. Now, what you can do is you have to find out the number of moles of the second component. Now, this is also easy for you because the number of moles, the mass is given to you 2 kg. You can convert this based on the molecular weight. Yes. You can convert this into the number of moles, which would be 2 kg divided by 342.2 kg mole or kilomole. Okay. So, because this is gram per mole, you can convert this to kg kilomole, and now you can plug this information. If you plug in this information, you get 207.3 liter per kilomole. So, that is the value you can get. Now, this is an approximation which you have made considering the fact that a very small amount of N2 is added to the system. But what about if you are interested in getting the partial molar property for the complete composition? Okay. So, let us now take an example and analyze it. So, consider variation of a molar property with the composition in a binary mixture 1 and 2. Okay. Let us look at this property, which let us say E. So, you have a property, let us say molar property, okay, which is we are saying let us say E. Okay. And you have some data, let us say like this, as a function of x1. Okay. And you can draw it. So, let us assume that you have you have data which you have evaluated in experiment, and you can plot it against the composition. Okay. So, let us assume that this is the data which you have. Okay. Now, this data is you could draw this because you have data along this curve. Okay. So, this is nothing but E. Okay. So, as of course, obviously you can see that when x1 is 1, which means this is E1 pure, okay, and correspondingly this is E2 pure. Okay. Now, but our interest is to find out the partial molar properties. So, let me just start with again the definition. So, the way we have written E mix is E minus summation Ni Ei. Okay, that is why by definition which we have written. Okay, E is a molar property of component I. We can divide this also by total number of moles and obtain something like in small e summation xi ei. So, in the case of the binary mixture, this is x1 E1 minus x2 E2. Okay. Now, so this is the definition by definition, right? Okay. Now, I can also write E as summation Ni Ei like this, and again I can write this E as, if you divide by total number of moles, this as Xi Ei. So, we have now this expression for binary mixture. I can connect this as x1 E1 bar plus x2 E2 bar. Okay. So, this is for binary mixture, right. I can now take a partial derivative of E with respect to x1. Let me try to do that, E versus x1. So, I got an expression of E1 bar plus x1 this plus del x2 by del x1 plus x2. Okay. So, we have this expression. Now, what I am going to do is to simplify this. In order to simplify this, when you look at this expression, the automatic intuition you should take is make use of Gibbs-Duhem relations in order to simplify this expression. So, what is a Gibbs-Duhem relation? Again, we go back to the Gibbs-Duhem relation. We know that Xi Ti equal to 0, or for the binary mixtures I can write this as, when I take a differentiation with respect to x1, when you look at this expression, which is a Gibbs-Duhem, that means this and this together will be 0. Okay. So, I remove. So, what I have left with is del E by del x1 is E1 bar plus del x2 by del x1 E2 bar. Okay. Now, this of course is minus. Okay. So, I have this expression which I am going to again write it again just for the sake of cleanness here. So, this is going to be del E del x1 is E2 E1 bar minus E2. So, this is one expression I am interested in. Then I have another expression, this one. So, this is let us say 1 and this is let us say 2. Okay. Now, I am going to play with this, because I can actually make use of the right hand side. Look at it, I can cancel some terms, and I have now one relation which is based on molar property, another based on the partial derivative of the molar property basically. Okay. And what we have the data of E versus x, okay, which we have plotted as a curve, and we can make use of its slopes. Slope is first derivative of E. Okay. So, if I use this one, if I multiply x2 multiply 2 by x2 and then add 1, the first one, what I am going to get is E plus, because I am going to multiply x2 here, this is going to be x2 del E by del x1, and the right hand side, since I have multiplied x2, that means this part will x2 here, this will get cancelled out. So, what remains is basically nothing but U1. So, this is one expression we got. Okay. Now, there is another expression we can get by multiplying, instead of x2, if I multiply minus x1 with 2 plus the first equation, and what I get here is E minus x1 del E by del x1 is equal to E2. So, this is my second equation. Okay. Now, look at this second equation, or the fourth equation rather. So, look at the first equation, what you have, E is nothing but the value, okay, y minus mx is equal to c. That is what this is the equation of line, isn't it? And what is the slope here? The slope is of course the first derivative of E. So, if you compare with a typical equation of line, then E2, which is a partial molar property, is nothing but the intercept, okay, of this, which essentially means if I have the value E and if I have the value of the slope at x1, okay, if I know of course x1, I can just take the subtract this two term and obtain my partial molar property, and similarly I can get it also for E1. Graphically it is much easier because it says that, well, E2 is nothing but a slope, okay, for equation which would be straightforward based on the relation which we have developed here. So, if this is the x1, let us say assume, which you are interested in, I take a slope, okay. So, the left hand side, the one which basically is the intercept, okay, would be E2 bar. Similarly, you can show that this is nothing but E1 bar. So, the graphically it's easy to evaluate if you have the data, but remember this E1 is at x1 and this E2 is also at x1. This is at x1. So, you keep changing the x1, okay. So, for example, you are interested in here, okay. So, that means you can draw it tangent to that particular point. So, this will be your E2 bar at x1 dash, this is E1 bar at x1 dash, okay. So, the graphically you can evaluate like this. Now, so let me just try to show this, we will try to do some examples later, okay, but let me just continue further from this and make some comments here. So, if you look at this equation and based on our analysis, E1 bar is nothing but when you put x1. So, if you take x1 to 1, it means a pure 1. So, E1 bar in that case would be nothing but E, okay, and this is nothing but E, because of course this is also true from equation 3, and this is E would be your E of pure 1, okay. Similarly, E for pure 2, okay. Now many times data may not be available of exactly absolute molar property, okay. Many times it will be available as the delta A mix, okay, the change in the molar property of the mixture, okay. So, if that is the case, if data are available for mixing, that means this is available, okay, delta E mix is available, okay, then in that case what we are able to evaluate is EI minus EI, we should be able to evaluate or get it from the experimental data, okay. So, you can use this expression what we have developed here, and using this expression we can extend this for delta E mix. So, delta E mix, by definition you know that we have to add, if you subtract E here, add minus summation Ni Ei, then this will become E mix on the left hand side plus x2 d by dx1. So, what I am doing is replacing basically E by E mix, okay, on the left hand side, and instead of right hand side just E1 bar, it will become E1 bar minus E1, okay. You can prove that, it is not difficult. Okay, so similarly here. So, that is what I said, when you have the data available for delta E mix, then you should be able to calculate the difference between the partial molar property and pure molar property for components I basically, okay. So, this is now the two relations we can get it if the data is delta E mix, okay. Now, in order to appreciate this, let us do an example. So, let me just write down the expression. This is the case where you have a binary mixture of benzene which is of course component, which is component 1 with cyclohexane, which is component 2. Okay. Now, we have been given data such as x1, and the value which is given is delta H mix, okay, which is in kilojoules per mole. Okay. So, let me just write down first the data which is available. So, this is 0.306, 0.67, 0.525, 0.83, 0.568, 0.8, 0.808, 0.53. Okay, so this is the information available to us. Now, the question is, how do we get the partial molar properties? Now, in this case, since this is delta H, what we are going to extract is basically H1 bar minus Hi, or Hi bar minus Hi. Okay. Now, the data is in a discrete form. We need to actually smoothen this out by considering an analytical form of the data in order to have an expression, so that we can draw it and get a first derivative of this data. That is most important. So, having analytical form is important. Now, this particular example is taken from a paper. So, how do we do that? Now, this is a trickier part, like given this, how to do that, because you have only 4 points. Okay, and if you know, if you have done this first derivative, you know that there is an issue with doing that. So, now, but the way we should think about is, what is the expression which can fit very well. Okay. So, in order to apply, we will be considering, so in order to apply or make use of this data, we will be considering an analytical expression. So, let us first understand the limiting condition of delta H mix. In order to get an analytical solution, you need to find a expression which also satisfies the limiting conditions. So, what is the limiting condition? So, when x1 goes to 0, what happens to delta H mix?
It would be H2 0.
Mix, delta H mix 0. So, delta H mix also would tend to 0. When x2 tends to 0, what would be the value of delta H mix? It's a 0. So, basically limiting condition is any of this composition, if it goes to 0, it means the other composition is pure. Okay. So, now we can come up with an expression considering this, a convenient function is basically some x1 x2 multiplication and some term. Okay. So, x1 x2 has to be there because it has to be 0 if we put any of them. But then considering that this is not a linear function, so it will be a quadratic in nature in some form, a polynomial function. So, we will be adding a plus b difference of x1 minus x2. Okay. Okay, so this is just a convenient form which we are writing it. Okay, there is a little bit of experience goes into that in coming of this expression, but having this expression now, these constants are a and b have to be evaluated. Okay, so how do you find out this constants? You can plug this equation, okay, and the data in some software. For example, Excel solver can solve a and b. Okay, it can iterate such that, or refine the values in a and b such that the data fits very well. Okay. So, it turns out this expression actually fits very well the data with A is 3.27 kilojoules per mole, B is 0.21 kilojoules per mole. Okay. So, this is using Excel solver. Okay. So, if you have not done that, you should try to make use of it. You can just plug in this value, this becomes your x and this becomes your y, okay, and basically plug in this expression, try to fit it, put a and b as a variable which you would like to vary in solver, and let the Excel does its job. You should get this expression. Now, since this model fits well. Now, I have this discrete data in a continuous expression now, which is basically the analytical expression. Now, I can find out H1 bar minus H1, which is nothing but delta H mix plus X2 del X1 so this is X2 del by del X1 delta H mix. Okay. So, this comes directly from our expressions which we have written here. Okay. So, here instead of E I am just putting H here. Okay. And similarly I can write it for H2 also. So, now delta H mix is known. I can take the partial derivative of x1 with respect to partial derivative of this expression delta H mix with respect to x1. What I get? X1 x2 a plus b x1 minus x2, okay, and this further can be simplified. All right. So, now further if I simplify, this becomes ax1 minus ax1 square minus bx1 plus 3b to bx1 cube. Okay. I can take the derivatives.
x1 is missing.
X1 is
In second line. Bx1 to x1 minus 1.
bx
Second.
this one b
Bx1
So
to
we have
x1
x1 into x2. So we have converted x2 into minus x1 and we have orbit of x1.
so here what is saying x1 is missing.
Yes. Sir.
Uh,
So we have x1, x2 into x1.
right, this is one b x1 minus x2 which is 2x1. Oh, okay, right, okay, yes, indeed the x1 is missing here, right. So, okay, so now this expression, if you take the derivative, it yields the following: delta H mix plus x2 a minus 2a x1 minus b plus 6b x1 minus 6b x1 square. Okay. Now, similarly you can also get the expression for delta H mix, okay, which will be like H x1 a minus 2a x1 minus b plus 6 b x1 minus 6 b x1 square, because this is same as this. Okay. So, you got basically the expression for h1 bar minus h1, h2 bar minus this one. So, now you have an expression. Okay. You know the values of x1, you know exactly delta H mix. Okay, so I can actually feel this. Now, the model which we have developed is basically analytical model, right? So, just to give you idea what was the fit after using the Excel sheet, I can actually plug in the values of the model for a given values here. It was 0.68, 0.82, 0.81, 0.53, pretty good, right? Now, here I can, using this model and these values, and this specific, you can directly use this model, directly use the data for delta H mix, and you can plug in the A and B and the X corresponding in order to get for this difference for component 1. Okay, you plug in here, and for component 2 for, okay, using this expression. So, this is how we can solve the problem based on simple experimental data available for the partial molar properties, okay, if the molar properties information as a function of the compositions are given. Okay, so now what I am going to do is quickly make 2 points. Okay, before we end, I would like to make another important point is that most often we just do not use only the delta H mix or E mix or so forth. Sometimes we also use excess information. Okay, so let me just define this excess mixing property. Okay, which is basically excess mixing property. Okay, this is E Tp minus E Im. Im is basically ideal mixture, okay, for the same. Okay, so in other word, Vx is right. So Vx would be your now. What we can do is we can also consider this as a delta of delta it. For example, let us say if I add this as E minus summation Ni Ei, okay, minus E Mi summation Ni Ei, then this would be corresponding to your delta V of ideal mixture, and this will be corresponding to delta V mix. Okay. So, what is the delta V mix for ideal mixture? Delta V mix is basically nothing but 0. Okay, delta U mix is 0, delta H mix is also 0, and we have also calculated earlier delta S mix is minus R summation Ni ln Yi, delta G mix or delta A mix is RT summation Ni ln Y. So, this is something which we have calculated earlier. So, based on this information, we actually can write Vx is nothing but delta V mix, because the other part is going to be 0, Ux is delta U mix, and Hex is delta H mix. Okay. Right. Now, we can also talk about Sx. Okay. Now, this is nothing but S minus Sim, which I can write as or as Im I can write as nothing but summation Ni small si minus Nr summation Yi ln Yi. So, I am just writing out the entropy of the ideal mixture. Okay. Okay, and this is nothing but your delta S mix. Okay, and this is nothing but your minus of delta ideal mixture mix, something like that. So, we can write this kind of expression. Similarly, I can write Gx is basically delta G mix minus RT summation Ni ln Yi, Ax minus RT summation Ni. Okay. So, this is something which I want to talk about as far as the excess property is concerned. So, last leg of today's lecture is to make a note of that the expression which we are writing for chemical potential do not hold, particularly when we talk about ideal gas mixtures, it does not hold for the real systems. Okay. So, I am just going to continue this and just talk about ideal mixture, that if you recall we have written mu I, okay, which is Tp and is nothing but partial derivative of G, and this is nothing but small gi Tp plus RT ln Vi. This is for ideal mixture. Okay. Okay, and this is nothing but mu I for pure Tp, okay, plus RT ln Yi, and this is nothing but mu I. Okay. So, this we know, this is what we have earlier talked about it. Now, we can try to get this expression with respect to some reference pressure. Okay. So, I can make use of del G by del P at T, which is nothing but by definition V. For an ideal gas, this is nRT by P. So, on similarly, I can also write del mu by del P T, and this I can write G by N P by T, and this is nothing but RT by P. If I integrate this expression P0 to P, I get mu Tp as mu Tp0 plus RT ln P by P0. Okay. So, we can, and this is for a component, let us say pure component, we can plug in here. What we get? We get mu I for an ideal gas mixture Tp n is equal to mu I pure T P0 plus RT ln Yp by P0, which is nothing but partial pressure Pi. Okay, so, this is the expression we got typically. Okay. Now, in general, this chemical potential with the way we have written that mu I is equal to mu I pure plus RT ln Y, these do not hold for liquids. Okay. So, for liquid, okay, so in general, especially for liquid mixture, having dissimilar component, mu I Tp n is not equal to mu I pure Tp plus RT ln, well, instead of Yi, since we are talking about liquid, we can simply say Xi. Okay. Now, this leads to the definition of activity. Okay. This leads to the definition of activity. So, the way we define activity is such that mu I Tp n is equal to mu I pure Tp plus RT ln Ai. Okay. And that is what we defined. This is an activity. Okay. And of course, for an ideal condition, ideal mixture, Ai is nothing but Xi. In this case, of course, we are talking about Xi because the liquid. So, Ai, if it is same, it means basically an ideal solution. Okay. So, remember this X and Y is our nomenclature, it just means composition. Okay. So, we defined activity coefficient to make these differences clear. Okay. Tp n, which is nothing but Ai divided by Xi. So, for an ideal mixture, gamma I is basically nothing but 1. Okay. So, I think I will stop here because this is the moment we will take, we will take this concept further in our analysis of solutions, and but this is just to introduce that what we have done till a couple of lectures was all about ideal gas mixtures, ideal solution mixtures, and here of course there is a lot of assumptions. Okay, for ideally for real conditions we have a deviation from the ideal conditions, and that is why we have introduced this kind of nomenclature. So, in the next lecture we will start up the volumetric property, and this part as far as the activity is concerned we will take up in the later part of the course. Okay. So, yeah, I will see you next lecture then.